So this is a homework problem from group theory, which was to compute the commutator subgroup of S3, the symmetric group on 3 letters. And so the commutator subgroup, this is the subgroup of S3 generated by the set of all commutators xy, where xy is defined to be x inverse y inverse x times y. So what could this be? So let's just look at some examples of commutators. So if x equals y, then this commutator is x inverse xx if x equals y, which is just the identity. So taking the commutator of an element with itself is the identity. And moreover, if xy equals yx, so if x and y commute, then the commutator of x and y, x inverse xy, xy is the same as yx, so that's x inverse yx. And these cancel, so we also get the identity. So we only have to consider commutators of elements that don't commute. And there are 2 possibilities. You could have xy equal to transpositions. So for example, if x is the transposition 1, 2, and y is the transposition 1, 3, then the commutator is x inverse y inverse xy. But for a transposition, the inverse is the same as the element. So this is just xy. So that's 1, 2, 1, 3, 1, 2, 1, 3. If you multiply 1, 2, and 1, 3, what do you get? You get the cycle 1 goes to 3, 3 goes to 2, 2 goes to 1, which is, suppose I let sigma be the cycle 1, 2, 3, and then sigma squared is the cycle 1, 3, 2. And sigma cubed is the identity, because if you go around a cycle of length 3 times, you're always back to where you started. So this is sigma squared, which is sigma to the 4th, which is sigma cubed times sigma. Sigma cubed is the identity, so this is just sigma. So the commutator of these 2 transpositions is sigma. And if I took the commutator of those 2 transpositions in the opposite order, I would get 1, 3, 1, 2, 1, 3, 1, 2. That turns out this is sigma, because 1 goes to 2, 2 goes to 3, 3 goes to 1. Sigma times sigma, this is sigma squared. So if I take the product of any 2 transpositions, I get either sigma or sigma squared. Right? If I take the product of, suppose I take x to be a transposition and y to be sigma 1, 2, 3, what is the commutator in that case? That's going to be 1, 2, 1, 2 inverse, 1, 2, 3 inverse, 1, 2, 1, 2, 3. That's the definition of commutator, x inverse y inverse xy. But the inverse of a transposition is itself. The inverse of 1, 2, 3 is 1, 3, 2 times 1, 2 times 1, 2, 3. Let's see. So this I have to calculate. What is this? 1 goes to 2, 2 goes back to 1, 1 goes to 3. So 1 goes to 3, 3 goes to 2, 2 goes to 1, 1 goes to 3. So that's this transposition. 3 goes to 1, goes to 2, goes back to 1. 3 goes to 1. So this, this commutator is just 1, 3. And in fact, if you do a couple of other calculations, you'll find that every element of S3 actually, let me just double check this because something here I find puzzling. So 1 goes to 2, 2 goes back to 1. 1 goes to 2, 2 goes back to 1. 1 goes to 3. So 1 goes to 3. 3 goes to 2, 2 goes to 1. 1 goes to 3. Three goes to 1, 1 goes to 2, 2 goes to 1, and 1 goes to 2. So 3 goes to 2. And 2 goes to 3, goes to 2, goes back to 1. So this commutator is 1, 3, 2. And in fact, when you look at all the commutators, you either get the identity, the 3-cycle sigma, or the 3-cycle sigma squared. So for S3, the derived group, the commutator subgroup, is just the cyclic group generated by sigma. So it's the identity sigma and sigma squared. Right? So this is just doing the calculation, and this is what you get. So you have to do a little bit of work, a little bit of computation in order to solve the problem. Right? So I don't know if I went through that too quickly, but if there are any questions, I can do it again or repeat any part of it.
Do it again.
Sorry, I didn't hear. I'll do it again.
Yeah.
So,
Or could you go over another example if it's not so much to ask?
sure, which one?
It could be any.
Well, there are a lot of problems. There are problems on group theory and there are problems on ring theory. So you have to,
Oh, okay.
I mean, I can pick some problems at random, but I'd rather pick something that someone has tried and had a question with.
Well, if someone else want to take something.
Maybe, Professor, the same question, but instead of put S3, maybe now S4 or similar example.
Well, the reason I use S3 is because the group S3 only has 6 elements and there aren't many commutators you need to calculate. But if you go to S4, that group has 24 elements. And that is a much, much, much larger calculation. And it might take me half an hour just to, or more, just to do all the computations you need to get the answer.
Can we do part B then? I think it's T3 or tau 3.
Let's see. So can you read the problem to me? I'm not sure that I have the same version of the notes that you have.
It was compute the commutator subgroup of the cyclic group tau 3 or T3.
Well, if we take a cyclic group, gamma n for any n, this is abelian if it's a cyclic group. So the commutator is the identity for all x and y in the cyclic group. So the only element in the commutator subgroup is the identity. And in that case, the commutator subgroup is just a trivial group consisting of only the identity element.
Oh, wow. That's surprising.
So for an abelian group, the commutator subgroup is always trivial. It's just the identity.
Oh, okay. So it's a group. Oh, shit. If you do it, you multiply 1 time.
Any other questions?
Yeah, please. Ask some questions on the fuckers. Shit. Do it again. Oh,
So let me continue with the study of rings.
fuck.
So this is, recall the definition. A ring R is a set with two operations, addition and multiplication, such that the following properties are satisfied. First of all, R under addition is an additive abelian group. Second, the multiplication is associative. That means xy times z is the same as x times yz. Third, there's a multiplicative identity 1. So it's an element you might call 1, such that 1 times x and x times 1 is equal to x for all x. And fourth, we have some distributive laws that x times y plus z is xy plus xz, and x plus y times z is xz plus yz. So a set with addition and multiplication that satisfies these properties is called a ring. So two basic examples are z, the integers, with the usual addition and multiplication, and M2 of R, 2 by 2 matrices. Again, with the usual addition and multiplication of matrices. So Matrix addition and multiplication satisfies the conditions of a ring, and integer addition and multiplication satisfy the conditions for a ring. Okay. Now, in an additive abelian group G, every subgroup H is a normal subgroup. And we defined G mod H as the quotient group. Right? G mod H is the set of all cosets of H with addition defined by, if you take the coset X plus H and the coset Y plus H, you can add them and define that to be the coset X plus Y plus H. And again, you have to spend a lot of time working through the definition of a normal subgroup and the properties of a normal subgroup to make sure that this is a well-defined definition of addition of cosets. But when you have a subgroup of an abelian group, you can always construct this quotient group. And we would like to do the same thing for a ring. So now suppose R is a ring, and let's just say we take H to be a subgroup of the additive group H, additive group R, because every ring is an additive abelian group. So every additive subgroup, you can always construct the quotient group X plus H, and we know this is a group, an additive group. But we want to find conditions on H such that R mod H is a ring, not just a group, but a ring with the obvious multiplication, we hope, that X plus H times Y plus H, you can multiply cosets and get XY plus H. So just choosing a subgroup doesn't necessarily do this. But the question then becomes, what additional properties would you have to put on a subgroup so that when you form the quotient group, it is in fact also a ring? And so let me just repeat what I just said using slightly different notation. We want to find conditions on a subgroup. Instead of H, I'll call it I. I'll write it like this, a subgroup I of R, so that the quotient group R mod I is a ring. And it turns out that a sufficient, and in fact a necessary and sufficient condition is the following. So I is called an ideal of the ring R if it satisfies the following two properties. First, I is a subgroup of the additive group R. And second, for all X in this subgroup, and all elements are in the ring, if I take X and multiply it on the left by R, this is in I. And if I take X and multiply it on the right by R, this is also in the ideal. So an ideal of a ring is a special kind of subgroup. It's a subgroup which somehow is closed under multiplication by any element of the group. So here's an example. Suppose I let Z equal to, well, suppose I let my ring be the integers and let I be the set of all even numbers. So 2Z, first of all, is an additive subgroup. Because if you take two even numbers and add them, you get another even number. And if R is any integer and X is any even integer, then Rx and XR, they're the same because this is a commutative ring, multiplication is commutative. Rx equal XR is also even, right? If you take the number 10 and you multiply it by 3, you get 30. It's always an even number. An even number times every integer is even. So a very nice, important example to keep in your head is just the even number sitting inside the integers. Because you multiply any even number by any integer, and it's always an even number. And I claim if you have an ideal, then multiplication of cosets is well defined. So the proof of that is just one line in the notes. So we have R is a ring, and I is an ideal of R. So suppose you have X plus I, that's a coset, and that's the same as X prime plus I. And you have another pair of cosets, X plus Y plus I, and you represent it also as Y prime plus I. So I have one left coset, which I can represent in different ways. To say that X plus I equals X prime plus I, this means X minus X prime is an element of I. And this means Y minus Y prime is an element of I. So we would like to say that the product of the coset X plus I and Y plus I is the coset XY plus I. But then this would also have to be the same as the product of the coset X prime plus I and Y prime plus I, because they're the same coset. But if we have these representatives of the cosets X prime and Y prime, this is X prime Y prime plus I. So these have to be the same. What does that mean? The coset XY plus I is the coset X prime Y prime plus I, if and only if XY minus X prime Y prime belongs to the ideal. But we can write, let's see, XY minus X prime Y prime. Let's be a little bit sneaky about this. This is XY minus X prime Y plus X prime Y. I just added and subtracted the same thing. Minus X prime Y prime. Right? I've just added 0. X prime Y minus X prime Y. From this and from the first two terms, but using distribution, this is X minus X prime times Y. And this is X prime times Y minus Y prime. but x minus x prime is in I. And y minus y prime is in I. So here I have an element of I, and I'm multiplying it by an element of the ring on the right. Here I have an element of I, and I'm multiplying it by an element of the ring on the left. But in an ideal, if you take any element of the ideal and multiply it on the left or the right by any element of the ring, you get something that's still inside the ideal. So this is a sum of two elements in the ideal. So this is in the ideal. Which means this multiplication of ideals is well defined.
Hmm.
Okay. So again, this is all written out, printed out and legibly in the notes. And so if you want to be able to define a quotient ring of a ring, you have to take not just a subgroup, but a subgroup with these additional properties, which in ring theory make it into what is called an ideal, or sometimes called a two-sided ideal. So if I is an ideal of a ring R, then R modulo the ideal is a ring called the quotient ring. So this is, again, a fundamental construction in algebra. But it's a simple generalization of the idea of a quotient ring in group theory. Right. Now, the second thing that we spent a lot of time studying in group theory were group homomorphisms. And there is the analog in ring theory of a ring homomorphism. So let me define what is a ring homomorphism. I'm trying to see where I defined it in the notes, and oh, there it is. Yeah, okay. So suppose we have two rings that R and S be rings. A ring homomorphism is a function f from R to S that satisfies the following three properties. First, it's a group homomorphism. F of x plus y is f of x plus f of y for all x and y in the ring. It's a multiplicative homomorphism. F of x times y is f of x times f of y for all x and y in the ring. And the third property is that it takes the identity in R to the identity in S. So f of 1 equals 1. Here, when I write 1, I should maybe say the 1 sub R. This means the identity element in the ring R And this is the identity element in the ring S. So a homomorphism sends 1 to 1. And so that's a ring homomorphism. And it has all of the nice properties you might hope to find. So what's the simplest example? Suppose we have the identity map. ID for identity from a ring to itself, which is simply defined by the identity sends X to X for all X. So f of X plus Y is X plus Y. F of X times Y is X times Y. F of 1 is 1. So this is always, the identity map is always a homomorphism. Suppose we have 3 rings, R, S, and T. And we have a homomorphism F from R to S, and another homomorphism G from S to T. Then I can always take the composite function, G composed with F, that sends R to T. So I claim that if F and G are ring homomorphisms, then the product G times F is also a ring homomorphism. And the proof, if you write everything down carefully, is as follows. If I take G composed with F of X plus Y, this means G of F of X plus Y. But because F is a homomorphism, F of X plus Y is F of X plus F of Y. And because G is a homomorphism, this is G of F of X plus G of F of Y, which is GF of X plus GF of Y. And if you want to check multiplication, GF of XY, this is G of F of XY. That's G of F of X times F of Y. That's G of F of X, G of F of Y. That's GF of X, GF of Y. So satisfies the multiplicative property. And for the identity, GF of 1, the 1 in R, is G of F of 1 of R. But F sends the identity in R to the identity in S, and G sends the identity in S to the identity in T. So the identity in R gets mapped to the identity in T. So this is a nice proof that the composite function of a ring of ring homomorphisms gives you another ring homomorphism. Here's an example of a ring homomorphism that you use all the time in high school algebra without using all this fancy terminology. So this is a theorem in the notes. So R of X, R is a ring, and this is the ring of polynomials with coefficients in R. So You know, if you take any ring R, the integers or the real numbers or the complex numbers or whatever your favorite ring might be, you can look at all polynomials with coefficients in R, and the rules for adding and multiplying polynomials give you a new ring, a bigger ring. So that S be a ring that could be equal to R or bigger. So S is a ring that contains R. So you have S and R is contained in S. Let little s be any element in S. So pick an element in S. So for every polynomial, f of x equal, let's say, summation I goes from 0 to m, a sub I x to the I in R of x. So right, this is a polynomial, right? This is a0 plus a1x plus a2x squared up to a sub m x to the m. So I want to define a function from the polynomial ring into S. So I'll call it epsilon sub S, which is going to send a polynomial to an element, a number in S. And we define it by letting epsilon sub S of the polynomial f be exactly what you get when you substitute S for x, a sub I s to the I. Right? So this is what we would call evaluate polynomial f of x at x equal to s. That is, you just substitute in s for this variable x, you calculate this number, that is epsilon sub s of f. And I claim epsilon s is a ring homomorphism. So this is a good exercise in polynomials. Let's see what we can do. Proof. So suppose we have two polynomials. F of x is summation a sub I x to the I goes from 0 up to m, and g of x is summation this typo in the notes, but I equals 0 up to n b sub I x to the I. So I have two polynomials. If I add them, f of x plus g of x, you simply add up the coefficients. This is ai plus bi x to the I goes from 0. I never said that these coefficients are all non-zero. So for simplicity, I can assume they have both summations go up to n. Let me just do it like that. So this is summation I goes from 0 up to n, ai plus bi xi. So this is the polynomial f plus g. So if I evaluate the polynomial f plus g at S, this is summation I goes from 0 up to n, ai plus bi, s to the I. But these are just ring elements. This is summation I goes from 0 up to n, ai s to the I plus summation I goes from 0 up to n, bi s to the I. This is just the polynomial f evaluated at S, and this is just the polynomial g evaluated at S. So epsilon of f plus g is epsilon f plus epsilon g. So the first property of a ring homomorphism is satisfied. What about the product? So the polynomial fg, this is summation I goes from 0 up to n ai x to the I, times the polynomial, I'll use a different letter, j goes from 0 up to n, bjxj. How do you multiply polynomials? You get a polynomial, say k goes from 0 up to at most 2n, x to the I, x to the j is x to the I plus j. If I and j go up to n, I plus j goes up to 2n. So x to the k. And when do I get a k? Whenever I plus j adds up to k. So you need to go sit down with some paper, take a couple of polynomials, f and g, multiply them together, and see that this is exactly the rule for polynomial multiplication. So epsilon sub s, let's say of f, epsilon sub s of g. If I evaluate f at s, I get summation. I goes from 0 up to n, a sub I, s to the I. If I evaluate the polynomial g at s, I get summation bj s to the j. Again, it's the same rule for multiplying. This is summation. K goes from 0 up to 2n. Summation over all I plus j equal to k, ai bj, s to the k. But that's exactly this polynomial evaluated at s. So the rule for multiplication is satisfied. And finally, if you take the constant polynomial 1, epsilon sub s of the constant 1 is just the constant 1. Sorry. Yeah. I mean, the identity in R is the same as the identity in S. So this is a ring homomorphism. So again, you do this all the time in calculus and pre-calculus. You take a polynomial, you evaluate it at a number, and f of 1 times f of s times g of s is the same as the product fg evaluated at s. Questions about anything? Theorem 3 is another example of a ring homomorphism. R is a ring. I is an ideal. And R mod I is the quotient ring. So define a function pi from R to R mod I by pi of x is the coset x plus I. So pi is a ring homomorphism. And the proof is really built into the construction of the quotient ring. Pi of x plus y is the coset x plus y plus I, which is x plus I plus y plus I. This is how addition of cosets is defined. This is pi of x plus pi of y. So this is the first condition for a ring homomorphism. Pi of the product is xy plus I, which we saw is x plus I times y plus I. So that's pi of x times pi of y. And pi of the identity in the ring R is 1 sub r plus h. And this coset is exactly the identity element in the quotient ring. So all of the properties of a ring homomorphism are satisfied. And this homomorphism pi from R to R mod I is called the canonical ring homomorphism. Right? And what is the perfect analog of the main isomorphism theorem for groups also holds for rings. So let's define the kernel and the image of a homomorphism. So let F from R to S be a ring homomorphism. What's called the kernel of R is all elements X and R such that F of X is 0. And what is called the image of R is the set of all elements F of X in S as X runs through the elements of R, or you could say it's all the elements Y in S such that Y equals F of X for some X in the ring R. So what in the notes is called lemma 5 says that if you have F from R to S, a ring homomorphism, the kernel of F is always an ideal in R, and the image of S is a subring. So the image of F is a subring of S. That's a subring contained in S. And F is 1-to-1 if and only if the kernel of F is just 0.
Sorry, Professor, can you repeat that last line again?
Yes.
Thank
The
you.
ring homomorphism F is 1-to-1 if and only if the kernel of the homomorphism F is just 0. The only element that maps to 0 is the 0 of the ring. And the proof goes as follows. So first I want to show kernel of F is an ideal. So suppose X and Y are in, let me call this K for kernel, or let me call it I. Suppose X and Y are in I and R is any element in the ring. So F of X equals 0 and F of Y equals 0 because they're in the kernel. So F of X plus Y is F of X plus F of Y. That's 0 plus 0, that's 0. So if two elements are in the kernel, so is their sum. And if I take F of X minus Y, that's the difference, but 0 minus 0 is 0. So the kernel is closed under addition and subtraction. F of 0 certainly equals 0 because a ring homomorphism is a group homomorphism, and a group homomorphism always sends the identity to itself. The additive identity is 0. So the kernel of F is a group homomorphism, but why is it an ideal? So if I take F of R times X, X is in the ideal and R is in the ring. Because F's a homomorphism, this is F of R times F of X. F of R is some element in S, whatever it might be, but X is in the ideal, X is in the kernel. So F of X is 0, and anything times 0 is 0. And in the same way, F of XR is F of X times F of R. That's 0 times F of R, which is 0. So the kernel is an additive subgroup of the ring, which is closed under left and right multiplication by any ring element. And that means the kernel is an ideal. Right? So that's the proof of the first part of this lemma. I want to prove the image of F is a subring of S. So let Y1 and Y2 be in the image of F. That means that there exist X1, X2 in R with F of X1 equals Y1 and F of X2 equals Y2. But this means Y1 plus Y2 is F of X1 plus F of X2. But F's a homomorphism. This is F of X1 plus X2. So this is the image of some elements in R, so this is also in the image of F. So the image is closed under addition. And if I made this subtraction, still is in the image of F. So the image is certainly an additive subgroup. Is it closed under multiplication? Well, Y1, Y2 is F of X1, F of X2. That's F of X1, X2. So this is also in the image of F. So here we have S, here we have R, this function F between them, and sitting over here in S is the image of F. It's a certain subset of S, but this subset is closed under addition, it's closed under multiplication. F of 0 is always 0. And f of 1 is always 1. So 0 and 1 are in the image of f. So this is a subring. If the distributive law works in S, it works for any elements contained in S in the image. So this is a subring. So that proves the second part. And if x1 and x2 are in R, and f of x1 equals f of x2, sorry, x1, x2 are in R, f of x1 equals f of x2 if and only if f of x1 minus f of x2, which is f of x1 minus x2, is 0. Which means if and only if x1 minus x2 is in the kernel of f. So if the kernel of f just consists of 0, then the only way f of x1 equals f of x2 is when x1 minus x2 equals 0 or x1 equals x2. So if the kernel of f is 0, the function is 1-to-1. And if the function is 1-to-1, and f of x equals 0, then f of 0 also equals 0. So x has to equal 0. Because the only element, because there's only one element that gets mapped to 0, and 0 always is mapped to 0. So if x is mapped to 0, x is equal to 0. So the kernel of f consists only of 0.
Can you pull the paper down, Professor?
So from this, we can prove, remember we had proved in group theory what was called the fundamental isomorphism theorem for groups. And now we can prove the fundamental isomorphism theorem for rings. It says the following. Suppose f from R to S is a ring homomorphism with f of R, the image of f, and I equal to the kernel of f. So let me prove this. Let me prove the simplest case first. There's a slightly more general case that I prove in the notes, and I'll prove that in a moment. But so we have kernel of f is an ideal of R. So here I have my ring R, and I have this homomorphism f from S to R. But because I is an ideal, I have a quotient ring. And from R to R mod I have this canonical homomorphism. So I claim I can define a function f tilde from R mod I to S which is a ring homomorphism, and in fact, it's an isomorphism. And F is the composite of F tilde composed with pi. That is, I can construct a homomorphism from the quotient ring into S, which is not just a this is all true almost, but so F maps R into the range of R, which is contained in S. So if I look at the map F, it sends R into the range of F, into F of R, which is sitting inside of S. And this map from R mod I into F of R is in fact an isomorphism, 1 to 1 and on to. So there's a kind of obvious way F tilde has to be defined if this is going to be true. Namely, we want F of X to be F tilde composed with pi of X, which is F tilde of pi of X. But pi of X, that's just the coset X plus I. So we're going to have to define F tilde of X plus I to be equal to F of X. And the first question is F tilde well defined? So let's think for a second about what this means. So we must show that if X plus I equals X prime plus I, then F of X equals F of X prime. And why is this true? Well, X plus I equals X prime plus I if and only if X minus X prime is in the ideal, which is the kernel of F. So this is the case if and only if F of X minus F of X prime equals 0. But F of X minus F of X prime is F of X minus F of X prime equals 0, which is the same as saying F of X equals F of X prime. So the function F tilde from R mod I into F of R defined by F tilde of X plus I equals F of X is well defined. And now that we know it's well defined, the rest is almost automatic. F tilde of X1 plus H plus F tilde of X2 plus H, that's F of X1 plus F of X2. That's how we defined F tilde. But F's a homomorphism. This is F of X1 plus X2, which means this is F tilde of X1 plus x2 plus I, this should be an I here, not an H, which is f tilde of x1 plus I plus x2 plus I. So F satisfies the first condition, F tilde, of a ring homomorphism. F tilde of x1 plus I times F tilde of x2 plus I. That's f of x1, f of x2. That's f of x1 times x2. That's x1, x2 plus I. That's x1 plus I oops, sorry. This is f tilde of x1, x2 plus I. That's f tilde of x1 plus I times x2 plus I. So f tilde is multiplicative. And finally, f tilde of 1 plus I is f of 1, which is 1. Yeah. So f tilde of 1 plus I gets mapped to the identity. That's all we needed to show. So this f tilde is a homomorphism of rings. So let's draw this picture again. We have R goes to the image of F, which is f of R, contained in S under this function F. I have the kernel I of F, which is an ideal, and this canonical map, and I map F tilde from the quotient ring into f of R, defined by F tilde of x plus I, the coset, is f of x. F tilde of x plus I equals 0 if and only if f of x equals 0, if and only if x is in the kernel of f, which is equal to I, if and only if x plus I equals I. So the kernel of f tilde is just the 0 coset, 0 plus I, or I. So f tilde is 1 to 1. And it's onto, because any element f of x is the image. So f tilde onto, because x in f of R implies f tilde, sorry, f of x in f of R, f tilde of x plus I is f of x. So onto. So f tilde is an isomorphism. So in all of algebra, this construction of a quotient group and the fundamental isomorphism, the construction of a quotient ring and the fundamental isomorphism, these come up over and over and over again in algebra. It's a very, very ubiquitous construction. Now, in the notes, I prove a somewhat general, more general version of this. Again, we have a ring R a function into some ring S. The image is contained in S. I have I is equal to the kernel of F. And I take an ideal J that contains I. So I is contained in the ideal J, but J is an ideal. So I have a quotient ring R mod J, a canonical homomorphism pi, and I want to define a function F tilde from the quotient ring into this image that makes this composite function equal to F. So I want to define F tilde of X plus J equal to F of X. And to show this is well defined, we have X1 plus J equal X2 plus J means X1 minus X2 is an element of J. Sorry, I said something slightly backwards. I want the ideal I contains J. So over in R, I have my ideal I, and inside I is J. So if X1 plus J equals X2 plus J, if these two cosets are equal, that means X1 minus X2 is in J, which is contained in I, which means F of X1 minus F of X2, which is F of X1 minus X2, is 0. So F of X1 equals F of X2, which means F tilde of X1 plus J equals F tilde of X2 plus J. So this is a well-defined map. And once you know this map is well-defined, the proof that this is a ring homomorphism is exactly the same as the proof I gave a moment ago. Again, this is already familiar to you in the simplest example. Suppose I take R, the ring, to be the integers, and the ideal to be the set of all multiples of M. If you take a positive integer M and you look at all multiples of M, right? So this is 0, plus or minus M, plus or minus 2M, plus or minus 3M, and so forth. This is an ideal. And we have the quotient ring Z mod MZ. This is congruence classes mod M. And if you have any homomorphism from Z into a ring S, and the kernel is MZ, then there's a function F tilde from this ring of congruence classes into S. Right? So F is a ring homomorphism, and its value at any integer really only depends on the congruence class of the integer. So you have this. This is an example of the theorem. Any questions about this? So there's one more result in this section that I want to show. So in the notes, I think this is theorem 5. So we have a ring R prime, and sigma is a ring homomorphism. But now, whenever you have a ring, you have the polynomials with coefficients in the ring. So I have this polynomial ring. It's a polynomial rings. I have polynomials with coefficients in R, and I also have polynomials with coefficients in R prime. And I claim that there's a homomorphism sigma tilde from this ring of polynomials to this ring of polynomials, defined as follows. So for a polynomial f, or f of t equals summation a sub I t to the I goes from 0 up to m. Let sigma tilde of f be the polynomial where you apply sigma to all the coefficients, sigma of a sub I t to the I. And I claim this sigma tilde defined like this is another ring homomorphism. Well, this is really just an exercise, again, in the formula for multiplication of polynomials. So here I have f of t. Suppose I have a polynomial g, summation j goes from 0 up to n, b sub j t to the j. If I multiply f times g, that's a sum. K goes from 0 up to m plus n, t to the k, and the coefficient of t to the k, you look at all pairs I and j, which add up to k, ai, bj. That's the product. So sigma tilde of fg is summation, k goes from 0 up to m plus n, sigma tilde of summation ai, bi, t to the k, ii, bj, I plus j equals k. Sorry, sigma. This is summation, k goes from 0 up to m plus m. Because sigma is a ring homomorphism, summation I plus j equals k, sigma of ai, sigma of bj, t to the k. And this is exactly summation sigma of ai, t to the I, times summation sigma of bj, t to the j, which is f tilde, which is sigma tilde of f, sigma tilde of g. So again, the only way to understand what's going on is to find yourself a quiet place and a lot of paper and time, and just go through these things line by line and symbol by symbol, and working out maybe a few simple examples. Right? That's how you get it to work. Maybe just for fun, I'll pick make one example. Suppose I take R equals Z and R prime to be Z mod 3Z. And I take sigma of a number A is the coset A plus 3Z. Suppose f of t is 1 plus 2t, and g of t is, let's say, 2 plus t squared. I'm sorry, this is. So what is f times g? That's f of t, g of t. If I multiply these two polynomials, what do I get? I get 1 plus, oops, sorry, I get 2 plus 2t get 2, sorry, 1 times 2 is 2, 1 plus 4t, 2 plus 4t plus 1t squared plus 2t cubed. Right? That's f times g. So sigma tilde of f is, let me write a bar over something. A bar means a plus 3z. So sigma tilde of f is sigma of 1 plus sigma of 2 times t. That's 1 bar plus 2 bar t. And sigma tilde of g is sigma of 2 plus sigma of 1 t squared. That's 2 bar plus 1 bar t squared. And sigma tilde of f times sigma tilde of g. So I'm multiplying these two polynomials, 1 bar plus 2 bar t, 2 bar plus 1 bar t squared. That's equal to 2 bar plus 4 bar t plus 1 bar t squared plus 2 bar t cubed. But 4 bar is 4 plus 3z, which is the same as 1 plus 3z, or 1 bar. So this is 2 bar plus 1 times t plus 1 times t squared plus 2 bar t cubed. And what's sigma tilde of fg? That's 2 bar plus 4 bar t plus 1 bar t squared plus 2 bar t cubed. It's exactly the same thing. This is 2 bar plus 1 bar t plus 1 bar t squared plus 2 bar t cubed. Right? They're equal. So this is an example of what we're doing. I mean, it may seem complicated, but it's really just high school algebra when we're dealing with polynomials. Okay. Any questions about this? All right. So this was section 2 in the notes on ring theory. And on Wednesday, I'm going to talk about section 3, which is fields of fractions. And that's exactly as far as the midterm exam, which is in 2 weeks, we'll cover. Okay. Questions about anything?